Good morning, children. In the last class, we were discussing about which are the rotational analog of force and that of linear momentum. And then we studied that the rotational analog of force actually it is torque, and that of the rotational analog of linear momentum that is actually angular momentum itself. So next we are going to study about some more terms related with the rotational motion, which is actually the rotational analog of a body which is in linear motion itself. So like that, one of the important term which is or one of the important question it arises whenever we are considering a rigid body which is in rotation is what is actually the rotational analog of mass of a body itself. So the rotational analog of mass of a body is actually known as moment of inertia. So moment of inertia is actually the term which is used to represent the rotational analog of mass of a body. And then what is the expression for that? And the moment of inertia of a body, it is usually represented with the letter I. And what is moment of inertia? And in order to get an expression about the moment of inertia of a body, which is actually the rotational analog of mass of a body itself, first of all, we can find the expression for kinetic energy of a body which is in rotation. And we studied that while discussing about the rotational motion of a body, we studied that when a body it is in rotational motion, we consider the simple concept that means the rigid body is rotating about one fixed axis. So all the particles in that body it is rotating or following a circular path itself. So here in this case, in order to find the moment of inertia of a body, whenever we are calculating the kinetic energy of a particle, means we know the expression to find the kinetic energy is that is half mv square. Am I right? And where v is actually the formula, or that is actually the velocity. Velocity means that is actually the linear velocity. But whenever we are considering a particle which is in rotational motion, that means when a rigid body it is rotating about a fixed axis, all the particle in this body it is following a circular path. And this body it is rotating about a fixed axis with an angular velocity omega. And if this particle, when you choose this is at a distance r away from the axis of rotation, the relation connecting between the linear velocity, the radius or the position of the particle from the axis of rotation, and that of the angular velocity omega is, we studied that v is equal to r omega. V is equal to r omega itself. Therefore, in order to find the kinetic energy of a particle with mass m, if the particle is I particle, that means a rigid body means there are the presence of n number of particles are there, and suppose we are choosing a particle with mass m, and that is actually the ith particle, therefore mi, and its position vector it is ri, and that is moving with an angular velocity omega I. But whenever we are considering a rigid body which is rotating about a fixed axis, the angular velocity of all the particles will be same. Therefore, you can just choose it, that is omega itself. So, whenever you are using this relation connecting between the linear velocity, the position vector, and that of angular velocity in this formula of kinetic energy, you can write the kinetic energy of a particle with mass mi as that is equal to mi ri half mi v square. V means r omega, therefore ri omega the square. But here we are not writing it as omega I. Why? Because here we are considering the case in which a rigid body it is rotating about a fixed axis, means all the particle in that rigid body is rotating with a constant angular velocity itself. Therefore, you can write the formula as kinetic energy is equal to half mi Ri square omega square. So, this term, this is actually the rotational analog of the linear velocity. This is linear velocity, and in the expression of the kinetic energy of rotational motion, here this is the rotational analog of the linear velocity. But what stands for the mass m here? Instead of m, here comes the factor what? Mi Ri square. And this term mi Ri square is actually represented with the letter I, and which is actually known as what? The moment of inertia. Instead of considering the simple mass, the position of that mass is also want to represent it. And that is actually known as the moment of inertia of that body itself. So, you can write the expression for kinetic energy as half I omega square. Here, this I plays the role of mass of a body in rotational motion, and that is actually known as the moment of inertia, and that is actually the rotational analog of mass of a body which is in rotational motion itself. Understood? That is why comparing this equation 1 with that of this equation number 2, this is linear velocity, this is the rotational analog of velocity, that is angular velocity. But instead of mass m, here comes the factor mi Ri square. Therefore, this is actually playing the role of mass of a body which is in rotational motion. And that is represented with a simple letter I. Therefore, you can write kinetic energy as that is equal to half I omega square, where I is known as the moment of inertia of the body, that is actually plays the role of mass of a body which is in rotational motion itself. Understood? So that's about the term what? That's about the term moment of inertia. So moment of inertia is actually mi Ri square. This one here we consider a single particle with mass mi, an ith particle whose mass is mi and whose position it is Ri. So whenever you are considering that whole system, what is the total moment of inertia? You can write total moment of inertia means that is sigma I equal to 1 to n mi Ri square. And this I is varying from 1 to n, because that rigid body means that one consists n number of particles, and that mass it is varying from 1 to n, and that of the position of that particle also with respect to the about the axis of rotation, it is varying from 1 to n. And this is actually what? The moment of inertia of a body itself. And the moment of inertia of a body means that is actually the characteristics of the rigid body itself. It is not depends on the axis of rotation. It just depends upon the distribution of the particle from the axis of rotation only. Okay, so that's about the factor what? The moment of inertia of a body which is in rotational motion. So we can say that moment of inertia is actually the rotational analog of mass of a particle in which motion? Mass of a particle which is in linear motion itself. Okay. Next, we can discuss one example how to find the moment of inertia of some bodies. There is one table which is given in your textbook to study the moment of inertia of some bodies with particular dimension, that means symmetric dimension itself. For example, suppose there is a long rod of length, total length L, which is rotating about an axis passing through its center with an angular velocity omega, and both ends there will be the one mass it is attached, and the mass of the each of this ball is m/2, and each of this ball it is located at a length of L/2 from the axis of rotation. Then how can you calculate the moment of inertia of this system? So the moment of inertia of a body I means that is equal to sigma I is varying from 1 to n mi Ri square. So here how many particles are there? Two bodies of mass m/2. This is the axis. So if this is the origin, this is the first particle. This is at how much distance away from the axis of rotation? Ri means L/2. So whenever you are considering this particle A, its moment of inertia you can write it as m by 2, mass it is m by 2, ri square, ri means this distance, L by 2, therefore it becomes L by 2 the whole square, plus, which is the second particle? This is the second particle. What is its mass? Its mass is also m by 2. And this distance, that is actually L by 2 the whole square. So you can write this one as m by 2 L square by 4 plus m by 2 L square by 4. 2 times, therefore it becomes 2 times m L square by 8. 4 into 2, 8. So it comes as how much? M L square by 4. So this is the expression for the moment of inertia of a rod which is attached with a mass of m by 2. And this is a light rod. That is why we are not considering what is its mass. Okay. So like that way you can find the moment of inertia of a body of any geometry. And then in your textbook there is one table which is given which are the values of moment of inertia of a body with a different shape. And then the axis of rotation is also very important. Whenever you are shifting the axis or changing the axis, you can see from that table that the moment of inertia of that body is also varying. And in your plus 2 classes, no need to study the derivation, how to get the moment of inertia. That is actually by the process of integrations and all we want to do it. This is actually one of the simplest case which is discussed in your textbook. So this table you must copy in your textbook. You will get the question for your entrance exam and also for your class exams, which one you are going to write. What is the moment of inertia of a particular type of body. Okay. And then while discussing about the moment of inertia of a body, there is another one important term which comes, that is actually the radius of gyration. And it is represented with letter T. So, what is actually this radius of gyration means? While studying or while written the moment of inertia of a body I, we know that moment of inertia means that is mass of the body into r square, where actually r stands for the distance of that particular particle, which one you choose from the axis of rotation, or the distance of that body from the axis of rotation. In all the cases, the axis of rotation of that body will not be inside that body. In some cases, we are choosing the axis of rotation outside that body also. So, if moment of inertia I is equal to mr square, where r stands for the position of the particle from the axis of rotation, instead of that one, if you are writing that distance is k, you can write the formula as I is equal to mk square. And in your textbook, you can see that the moment of inertia of a body of a ring about an axis, like this it is, if it is having the radius r, means this is actually mr square. So, while comparing these two, this is the standard result. You are getting what is k square. K square is equal to r square. This is the general expression for moment of inertia, and this is actually the result of moment of inertia of a ring. So, while comparing this one, you are getting k is equal to r. And actually this k is actually known as the radius of gyration. And what is actually this radius of gyration means? That is a geometrical property of that body. And it is giving us the measure of the distribution of mass of the particle about that axis of rotation itself. What is radius of gyration? That one is actually a geometrical property which is giving us the measure of the distribution of mass of the particle about the axis of rotation itself. And therefore, this radius of gyration is actually the distance of the particle from the axis of rotation. So, k has the dimension of length. Dimension of length itself. And therefore, if you write SI will become meter. or cbse system if you are writing, that is centimeter itself. And then next, which one I am going to derive, that is actually not given in your textbook, but anyway you must study that. So what is radius of gyration and its expression means? We know that the radius of gyration is actually giving us the measure of the distribution of mass of the particle about the axis of rotation itself. So suppose we are considering a rigid body. It is rotating about this axis, and in this one there are number of particles m1, m2, etc. of mn, and each of this particle will be at a different distance from this one, r1. Here it is r2. The third particle will be at a distance r3, and this one will be at a distance of r. And suppose you are considering the mass of all the particles is same, individual particle m1, m2, m3, etc. is equal to m. What is the total moment of inertia of the system? I means sigma I equal to 1 to n mi ri square. So whenever you are writing this one, first particle with mass m1, its position mass, it is m itself we chose, therefore it become m r1 square. For second particle it is m r2 square plus m r3 square plus etc. of m rn square. But moment of inertia means we know that is the total mass of the system into k square, a general expression. So here m is common everywhere, so take it m outside. It becomes r1 square plus r2 square plus etc. of rn square. So if you multiply this one with n number of particles are there, n into m. So if you are multiplying, you must want to divide this one also by n. So n is the mass of individual particle. If you are multiplying that one with the total number of particles, you will get the total mass into this bracket, r1 square plus r2 square plus etc. of rn square divided by k. So while comparing these two formula, what is k stands for? Radius of gyration, which gives actually the measure of the distribution of the particle about the axis of rotation. So k square is you are getting, that is equal to r1 square plus r2 square plus etc. of rn square divided by n. So what is k? K is actually root of this one. Therefore, it is square root of the position of that particle. So k has the dimension of length, therefore it has the unit of m, and it depends on, it is a geometrical property of that body itself. Okay, so that's about moment of inertia and that of radius of gyration. So next we want to study about the kinematics of rotational motion about the fixed axis itself. The axis, it is not varying, fixed axis. So in that first part of your physics, that means in the volume 1, in the same first chapters, you people studied about the kinematic equations of motion in a straight line. You people studied about the equations of motion. So equations of motion, there we discussed about, as in the case of a single point mass, a point body itself. So whenever we were discussing about a point mass, we just want to consider the linear motion of that particle, and in that cases we can write the equations of motion of a body as v is equal to u plus at, where v stands for the final velocity of the body, u stands for the initial velocity of the body, a stands for the acceleration of the body, and t stands for the time taken. And the second form equation, you people studied that s is equal to u t plus half at square, where s stands for the displacement and all other factors has the same meaning. And the third equation of motion, you people written that is v square is equal to u square plus 2as itself. So Whenever we want to write these formulas into the terms of rotational motion of a body, we just want to consider the rotational analog of linear motion itself. These are the terms we are usually using as in the cases of an object which is in linear motion itself. But we know that as in the cases an object which is in rotational motion, V and U stands for velocity of a body which is in linear motion. But whenever we are considering the rotational motion of a body, a simple particle if we are considering, if this is its original position P1, after some time if that one reaches to a point P2 means we are considering this angle theta, because that body turned through an angle theta, or instead of the displacement S, we want to consider the angular displacement theta itself. Understood? And if displacement is S and V and U stands for the velocity of that body, instead of linear velocity we want to consider the angular velocity omega. But V stands for the final velocity omega and U stands for the initial velocity, therefore we can write that is omega 0 at a time t equal to 0 itself. In the same way, here the particle it is, therefore its angle it is at 0 position theta 0, and when that one reaches to this position theta, the displacement S means initial, final minus initial, theta minus theta 0, like that also you can do it. Angular displacement d theta, this is actually d theta, and time t itself, and a means angular acceleration. What is the rotational analog of angular acceleration? That is alpha. So how can you write these formulas into the rotational concept? V means final velocity, that is omega, equal to initial velocity omega 0 plus a, therefore alpha. And S means displacement, therefore you write that is equal to theta minus theta 0. Usually people were writing x2 minus x1, but x2 instead of x2 and x1, or x minus x0 instead of that one angled, therefore theta minus theta 0, that is equal to u means initial velocity omega 0 into t plus half alpha t square, and v square is equal to u square plus 2as, therefore omega square is equal to omega 0 the square plus 2. A means alpha, displacement theta minus theta 0. Once if initial position you are considering it as 0, you just write theta, like that way also you can write it. These are actually the kinematic equations of rotational motion itself. Understood? Next we are going to the comparison between the rotational motion and that of the linear motion. So before that we want to discuss some terms into the terms of the rotational motion. So we actually know that is first we are going to find the expression for work done into the terms of torque. That is, we know that when an object it is in rotational motion, instead of force we are using the rotational analog torque itself. Force is F, torque is using the letter tau itself. So we know the expression, actually the work done is W. W means F dot dx. So we want to get an expression for the work done by torque means instead of force it is torque tau. Instead of linear displacement, angular displacement d theta. That is actually the relation we want to get. So how we are getting the derivation? It is given in your textbook, so we can. So suppose we are considering a particle at this point P with position vector r, and on this particle there is the presence of a force, it is acting F, like this. So this position vector r, when you extend, this force F and that of position vector are made here an angle alpha. That is an angle alpha, not angular acceleration, just a notation. And because of this force, this particle, it is rotating in this direction. So this, from this point P, the particle reaches to another one position P dash, means this particle has a linear displacement here, ds, and the direction of the linear displacement is tangential to it. And this linear displacement and force made here an angle phi. That is angle phi. And this position vector r swept here an angle d theta. Understood? The particle P, on that one there is a force it is applied. That particle is describing a circular motion, and after some time that one reaches to this position P dash, and by the time there is a linear displacement, and the force and position vector made here an angle alpha, and force and that of the displacement, this is the direction of displacement, linear displacement made here an angle phi. So what is the work done by the particle? Work means force into displacement, F ds or F dot ds. But what is ds here? This ds is the linear displacement here, but that is actually part of this circular motion, and that is related with the d theta and this radius r. Angle is equal to what? Angle is equal to r by radius. Therefore, you can write d theta is equal to ds by r, or ds is equal to r d theta. Therefore, F dot r d theta. So what is A dot B? A dot B is actually AB cos theta. So F and r d theta dot product, F r d theta, force and r displacement, F dot ds, displacement. What is the angle between force and displacement? It is phi. Therefore F r d theta cos phi. But force and position displays r vector here, F dot ds, therefore force and displacement, angle it is phi. But whenever now you are writing here, there comes force and position vector. So force is this one, position vector is this one, therefore the angle it is alpha. So whenever you are writing that one, you can see here phi and alpha, phi plus alpha is 90. So what is phi? 90 minus alpha. So what is cos 90 minus alpha? That is sin alpha. So you can write this expression as F r d theta sin alpha. So you can write this is F r sin alpha of d theta. What is force into displacement into sine of the angle between the two? That is torque. What is torque? Torque is actually r cross f or r f sin theta. For theta is the angle between r and f. But here alpha is the angle between r and f. Therefore this is torque, tau dt. Therefore this is the expression to find the work done by a torque itself. I said no, we want to get this expression. That is work done by a body which is in rotation is W equal to tau d theta. Rotational analog of work formula expression. Term is work itself. So if you know the formula of work, what is the expression for power in rotational motion? Power means rate of doing work, dW by dt. Therefore it becomes d by dt of tau d theta. So it becomes tau into d theta by dt. What is d theta by dt? That is omega. Therefore, power P is equal to I omega. We studied that formula for power is in linear motion. This is rotational. And linearly we studied that power P is the rate of doing work, that is force into dx by dt. That means F into V. Rotational analog. Force in the rotational analog torque, velocity in the rotational analog omega. So this is the rotational analog of the expression for power itself. And then one more relation or formula it is there in order to show the power of a body. That is, whenever body which is in rotational motion, there is no any internal force it is there, only external force it is acting on that body. Therefore, whatever energy it is there in that system means that is actually used to increases its kinetic energy. Therefore, work is actually equivalent to what? Kinetic energy itself. So, whenever you are writing the expression for power, it is time rate of change of work. Work means that is kinetic energy. Kinetic energy means in rotational motion, the formula of kinetic energy is half I omega square. We already derived it while deriving what? Moment of inertia. Half mv square, where m stands for mass, but instead of mass, the rotation analog of mass, it is moment of inertia. And instead of velocity, angular velocity. So, half is constant, moment of inertia of a body is also a constant, omega is varying with increasing kinetic energy, therefore d by dt of omega square. But what is d by dt of omega square? For that, in differentiation, there is a rule. What is d by dt of x raised to n? D by dt of, where n is any power. D by dt of x raised to n means n into x raised to n minus 1. X is varying now, therefore dx by dt. So what is d by dt of omega square? D by dt of omega square means x raised to n means n. Therefore omega square instead of n it is 2. Therefore 2 omega n minus 1. Therefore 2 minus 1 d omega by dt. Therefore it becomes 2 omega d omega by dt. Substitute this one here. This become half I 2 omega d omega by dt. So 2 and 2 cancel. So power P is equal to I omega. What is d omega by dt? Time rate of change of linear velocity, that is angular acceleration. And just now in previous case we derived power P is equal to tau force into tau omega. Therefore tau omega is equal to I omega of alpha. So what is torque? Torque tau equal to I alpha. This is torque means rotational analog of force. I means rotational analog of mass. Alpha means rotational analog of linear acceleration. So this is actually the rotational analog of the formula F equal to ma, which is actually Newton's second law. So in similar way, we can write all the formula of a body which is in translational motion into which concept rotational motion, if we know which are the rotational analog of linear motion itself. Therefore, there is a comparative study it is given in your textbook. That table you can copy in your textbook, from your notebook. So 2 homework I set. Homework table of moment of inertia, table of moment of inertia, and comparative study of rotational motion and linear motion. So in linear displacement S, in rotational motion it is theta, and then linear velocity V, rotational velocity omega. In linear alpha, here it is alpha, here it is, this is linear motion, this is rotational motion. And then torque, force, here it is torque, and then here it is mass, here it is moment of inertia, and here kinetic energy is half mv square, and here it is half I omega square, and here the power P is and here force it is ma, here the torque it is I alpha, mass, moment of inertia, kinetic energy, power. Power P is equal to F into V, here it is tau omega, and linear momentum, mass into velocity, here it becomes I omega. So this is the comparative study between linear motion and that of rotational motion. So read your textbook properly. Okay, thank you.